realize that there's a ceiling on how much we can actually know. Some of which we'll get into in the quantum section. All right, when we first started talking about light, did I do Maxwell's equations?
Yes.
Okay, so I came by, I showed you what the equation for the speed of light was.
I believe so.
I might need a refresher, but,
So that was the equation. That's what Maxwell came up with in 1865. I should remember that. End of our Civil War, he was going up with this stuff. Maxwell was British, by the way.
Maxwell's equation for light.
So the equation for the speed of light. At this point, 1865, he comes up with this, makes the speculation that light might be an electromagnetic wave, and which turned out to be true. This is the point when it was sort of confirmed that electric fields actually do exist. Because before that, it could have just been a mathematical convenience. Unknown whether actually a physical meaning or whether it's just, a shorthand for a lot of other stuff. Physicists looked at this and they said, wow, that's really cool, but there's a mistake. And did I talk about the mistake? The mistake. I guess not. All right, so what's wrong with this? This is his formula for the speed of light. Why would physicists look at this and go, there's something wrong?
What are the variables?
These have been found experimentally at this point. Epsilons of naught, this is speed of light in free space. If it were going through a material or some medium, you would drop the zeros and there'd be other values for that. But in free space or a vacuum of space, the epsilon sub 0 is 8.85 times 10 to the negative 12 coulomb squared per Newton meter squared. And mu sub naught is known as the permeability of free space. And this is 4 pi times 10 to the negative 7th Tesla meters per ampere. So the value from mu sub naught in SI units is exact. This one is, I rounded off. And at this point, you can actually find this value because speed of light has an exact value right now. Mu sub naught has an exact value, so you could actually calculate epsilon sub naught. All right, however, what's wrong with this? Or what potentially could be wrong with what Maxwell came up with?
I asked the question of the variables because I thought that was the problem.
Nope, that is not the problem.
Speed of, how do you find the speed of light?
Experimentally?
Yeah, experimentally.
You bounce it off a whole lot of mirrors. There's actually, the technique that they did was you basically shine a light against something and bounce back and see how long it takes to get there and back. Now, the way you would do that is a stroboscope. Did I talk about this part? I can't remember what I did that when I first did light. Okay.
Yeah, I don't know.
Okay, the first technique that was used was by Galileo to try to find the speed of light experimentally. He basically stood a far distance away from someone else. He took a lantern, he opened up the lantern and closed it. The person on the other end saw the light, opened up, closed it, and they timed how long that took. Then they moved farther away, assumed that their human reactions would be the same, and then they tried to calculate the speed of light that way, taking into account the fact that most of the time was spent with people opening and closing. But if human reaction time was identical, you could calculate how long it took light to actually do that. What Galileo came up with was that if light is not infinitely fast, it's very, very fast. So, didn't quite work out. So, the biggest breakthrough is you take a wheel with a bunch of cogs in it, closer together than what I'm drawing here, all the way around. You rotate this. You shine light, so I've got that wheel rotating, and I have a light source over here, and a mirror. Now light is going to go through in between two of these. As you rotate this faster and faster, eventually that light is going to get blocked, because by the time the light comes back, this is now covering up where it would have come back. And then you keep rotating it even faster until it shows up again, because by that time, it's going on the right side of this cog, and then we'll come back on the left side of that cog. And so from that, you know how fast you're spinning the wheel, you know what that distance is, so you can calculate the time that is passed for the light to go wherever and back. That's basically how they first came up with the experimental value for the speed of light. Then, at that point, it's just a matter of more sophisticated. So, bigger cogs, bigger gear ratios, you can spin it, it's easier to spin it faster, or you have more mirrors for it to bounce off several before it comes back. That was the experimental.
I just don't know, I don't know the answer to that question.
Okay, so open it up though. I have a leading question that I think will give a big hint here, but I was hoping someone might think of it before I do that. All right, so my leading question is, how fast are you moving right now? What is your speed?
The same speed with the Earth rotating.
You said the speed of the Earth is rotating?
Yes.
Is that what the police generally pull you over for speeding?
Is it?
You're going a couple thousand miles an hour here.
Yeah, it's over 1,000 kilometers per hour.
So,
Respect to university. I don't know.
all right. So ultimately, speed, everything we dealt with up till for speed is relative to what? Where does that show up in this equation?
It is relatively to the university or the Earth, maybe.
No, it's not relative to the Earth, unless these were relative to the Earth, but they're not.
So it's relatively to university.
Or universe?
Yeah, the universe.
Except is there, well, that will be taken care of in just a moment. So if this is a look at that and said, you're missing a reference frame, it's not in there at all. Lorentz then spent the next, I don't hear of Lorentz really doing much else other than this. I'm sure he did other things, but Lorentz then jumped through hoops to try to figure out, to explain why they didn't show up here. But he missed a different conclusion that Einstein came up with. Einstein said, the reference frame's not here because there is no reference frame. The speed of light is constant regardless of the reference frame. That was the leap. Lorentz could have developed special relativity if he had just accepted that. A lot of the math that is used in special relativity comes from Lorentz. But he wouldn't make that last leap. Think of the implications here. If the speed of light is constant, now what I mean by regardless of reference frame, if you're traveling, that's sort of what Kong was talking about, if you're driving down the highway and the policeman has a radar gun standing on the side, clocks you, and you're going 50 miles per hour, that's relative to the policeman. If the policeman is in a car behind you, going 50 miles per hour while you're going 50 miles per hour, and he pulls out his radar gun and clocks you, you'll be going 0. How fast you're going depends on how fast the observer is going. Or reword that. How fast the observer says you're going depends on how fast the observer is going, or the reference is going. In everyday life, we generally consider the Earth as not moving. It's all a reference to the Earth. But you could take into account the fact that the Earth is spinning. The Earth is orbiting the Sun. The Sun's going around the middle of the Milky Way. The Milky Way is moving in itself. Here's the implication. This is a thought experiment. We have what I call the lab frame. In the lab frame, you have a box that's moving to the right. The box is going to emit a pulse of light. Now, because the box is moving off to the left, that pulse of light will have a speed off to the left. So that light is gonna bounce against the mirror. This is the mirror up here. And then bounce back down and hit the box again. In the box frame, the light just goes up and comes back.
In a straight line. In a straight line.
Yes, yes.
Yes.
From the box's point of view, they basically picture someone's in the box, they shine the light goes up, hits the mirror, comes back. On the side, because the box is moving, from the side view, the light is going at an angle, it has whatever speed it had going up, plus this component to the right, it'll come back. Right. Any questions or other questions about what's going on here? All right. What is the formula for speed?
Distance or time?
Yeah. If the speed of light is the same, no matter which case you're in, what is the implication?
That the box is moving at the speed of light.
No, not the box. The box is moving at some speed v. Alright, the thing about this, the distance from the box to the mirror is the same. Let's go ahead and just call that h. The light moves more in which frame? Lamp frame or box frame?
The light, if the speed of light is constant, so the light should travel in the box frame. I mean in the top one.
They're both moving at the same amount.
Oh, okay, let's get back to I had several questions on the floor here, so let's narrow it down. So the light's gonna travel farther in which frame?
Left or?
Okay. Yeah, you threw some extra explanation in there which didn't seem to fit with that, that's why I got confused. Alright,
Okay,
so it is travels longer here than it does here. Here it's just traveling a distance of 2h, here it's traveling, well, the hypotenuse of that triangle plus the hypotenuse of that triangle.
All right.
So the distances are not the same. But if the speeds are the same of the light, not the box, but the speed of the light is the same, what else must be true?
If the speed is the same, so the distance traveling is the same.
No,
So the distance should be the same?
if the,
Yes.
But the distances are not the same.
no, if the speed is the same, but the distance is not the same, then the time can't be the same.
That is the implication. The time is not the same.
The time not the same.
That was the really truly revolutionary aspect. Well, that's T1, this will be T2. They can't be the same. And much to everyone's delight, let's do a derivation. So the speed of light, c, is equal to the distance over time. So in the bottom case, that's the simpler one. The distance traveled is just 2 times h. So in the bottom case, so the box frame, this is the distance of 2 times h, and the time I'm just labeling as t2. In the lab frame, the distance that's traveled, well, I've got a triangle here. The distance that the box travels here, this full distance right here, is just how fast the box is traveling times the time, so this is vt1. This distance times time. One of the nice characteristics of special relativity, which is what we're doing right now, is that acceleration is zero. If you get into acceleration not being zero, you're now branching into general relativity, which is a huge pain in the butt. All right, so in the first case then, so this was the box frame, this is in the lab frame. The distance traveled is, well, I've got a triangle there. The height is h. This distance right here is 1/2 VT1. And so my hypotenuse is the square root of h squared plus 1/2 VT1 squared. It's traveling two of those, so it's 2 times the square root of h squared plus 1/2 v, oh, that's in parentheses there, VT1, all that squared, divided by T1. I'm basically going to solve for h in the second equation and plug it into the first equation, because h, hopefully, is going to become irrelevant, and it will. So h is equal to 1/2 CT2. So now, that first equation, I have the speed of light is 2 times the square root of 1/2 CT2 squared plus 1/2 VT1 squared divided by T1. Ultimately, what I'm looking for is the relationship between the two times. And in doing so, we'll reveal a very important equation, one that will haunt you for the rest of the relativity bit. So I have C T1, 1/2, so multiplied by T1 divided by 1/2, but divided by 2 is equal to the square root of 1/2 CT2 squared plus 1/2 VT1 squared. Square both sides. So I got 1/4 CT1, C squared, we'll just keep it at 1/2 CT1 squared is equal to 1/2 CT2 squared plus 1/2 VT1 squared. I have 1/2 squared common to everything, so I'm just going to multiply everything by 4 to get rid of those 1/2 squares. And then I'm going to get the T1s on one side, because again, I want a relationship between T1 and T2, so let's get all the T1s on one side. So I'm going to bring this over here. So I'm left with C, a marker that is darker. There we go. CT1 squared minus VT1 squared equals CT2 squared. I'm going to factor T1 squared out here, so I have T1 squared, and then C squared minus V squared is equal to, oh, that should be a C squared there. C squared T2 squared. Dividing both sides by this because there's a common form for this. So T1 squared is equal to C squared T2 squared over C squared minus V squared. I'm going to multiply top and bottom here by 1 over C squared. And so I'm left with T2 squared over 1 minus V squared over C squared. And then take the square root. So T1, the lab frame, is equal to T2 over the square root of 1 minus V squared over C squared. All right, questions about how I got to there? Because we will be using this quite a bit.
That formula over there?
Right here.
Okay. So what was that formula? What would you call that formula?
Time dilation.
Oh,
Time dilation formula. All right, I'm going to change this slightly. That's the essence, that's the bulk of it right there, but let's get into some of the vocab. T2 was the time in the box frame, when the box was just sitting there. From the box's point of view, the box is at rest. I think it makes sense. From your point of view, you're at rest, the world just moves around you. The rest frame, so this is also known as the rest frame, also known as the proper frame. Recognize that anytime you find a mass of an object, you take an object, you put it on a balance, and you measure it so that the scale, the mass are all moving at the exact same speed. In other words, from your point of view, they're not moving. You're finding its rest mass. Rest is just a reference to, that is the value when it is not moving. So T2 is often listed instead as T sub P for proper. So we have T in the non-rest frame is equal to TP over the square root of 1 minus V squared over C squared. V over C shows up so much that they decided to come up with a new letter for it. So V over C is just the ratio of how fast an object's going with respect to the speed of light, and that's equal to beta. This is the beta. So I can say an object's moving with beta is equal to 0.9, and that just means that it's moving at 0.9 times the speed of light. And this 1 over the square root of 1 minus beta squared, so therefore this becomes TP over the square root of 1 minus beta squared. This shows up so often that it has its special name and is represented by a gamma. And this is known as the Lorentz transformation. Sorry, the Lorentz factor. Lorentz transformation is a little bit different. Then we'll use that. And so this can be written as gamma TP. So we have, in essence, under the principle of conservation of complexity, the fewer letters you have, the more meaning in each letter. But time dilation, which is what we're talking about here, the fact that time is different between the two, can be characterized by T, can be simplified into just that one simple formula right there.
No, I mean that formula over there that you just wrote.
This one, T is equal to gamma TP. And
that's
basically that.
Oh, okay.
So it's like a sort of a summary over on this side. So we have time in the moving frame is equal to the proper time over the square root of 1 minus V squared over C squared. Since beta is V over C, this can be written as time is equal to TP over the square root of 1 minus beta squared. And then gamma is 1 over the square root of 1 minus beta squared. So T is equal to gamma TP.
And V is just the speed of the object.
V is the speed of the object, C is the speed of light. Right, so there are some implications here, so. What happens if V equals C? If the box were going the speed of light in the lab frame, what would gamma equal?
Gamma is
0.
equal
Not 0.
No, 1 over 0.
if it's not, it's 1 divided 0.
Yeah.
Yes, and the math people still haven't figured out how to do that. They claim it's undefined, and I just say, they really need to get their work up and actually come up with a definition. Here's a case where math drives the thought. The prediction is if the speed of light is actually a constant regardless of the reference frame, constant in a vacuum, then the object itself can never go the speed of light because you get this thing which is undefined. If that is true, then the speed of light is a barrier. Anything that starts slower than the speed of light can never go the speed of light. And eventually it comes out that in order to actually go the speed of light, you have to be a massless particle. So we have a limit here. If I take a force and apply a force to an object in classical physics, if I apply a force to an object, it will accelerate. If I maintain that force, then it will keep accelerating and eventually get to however fast I want it to go. We now are in semi-classical physics where there's a barrier. I will not be able to get an object, no matter how long I apply the force, will not be able to get an object to actually exceed the speed of light. I can get closer and closer, but I'll never actually reach it. So does that mean Newton's second law is wrong? So Newton's second law?
Force is mass times acceleration.
Yep. Let's get rid of all the derivation pieces of it.
I'd say that it's correct for things that don't need to go insanely fast, like
So,
faster than.
Well,
Yes.
that actually will still hold with that. There's some other issues. But if I can apply, theoretically, if I can apply a constant force to an object, the acceleration is constant. But it's not. If acceleration is constant, then I should be able to get to, theoretically, any speed I want. The deal is that as something gets faster and faster, the mass starts to increase. And so if I apply the same force, and my mass starts increasing once I get to a certain, my mass increases as they get faster and faster, we just don't notice it until a certain point, then my acceleration will get smaller. And so that's why as you get closer and closer, you'll start to level out because the mass is not getting any, because the mass is getting bigger. Because in everyday life, we assume that the mass of an object is the mass of the object is the mass of the object. However, we're now saying, depends on how fast the thing's going. So this is when we distinguish between rest mass and mass. And the factor between, the difference between those two, gamma. Now, for some reason, they call this proper time and they call this rest mass as opposed to proper mass or rest time, and just the way the language worked. And we'll get in, I probably won't do the full derivation of this one, you're welcome. But I will get to a certain point where I'll at least set it up and then say a bunch of math occurs and you get this. All right, so let's take a look at the Lorentz factor here, gamma. So if beta is 0.1, so going 10% the speed of light, what is gamma? We'll look at this formula right.
1.054 approximately.
Okay. So about 5% more than 1. Which means the difference in the times is 5% off. Typically 10%, when beta is 0.1, this is the point at which physicists start to go, yeah, we probably should take relativistic effects into account. Less than 10% the speed of light, you tend to go, we'll just go ignore it. There's a major exception, when dealing with satellites where you do have to take into account, even though they are traveling much less than the speed of light, but we'll get to that. If beta is 0.5, what is gamma?
Yeah, 1.155.
So you're now 15% off, difference in time. You know, start to be somewhat noticeable. We'll do two more of these. If beta is 0.9,
2.294.
and then beta is 0.994. That's something that's we'll be using in just a moment.
9.142.
Right, so we have all these calculations here. Notice that gamma gets larger and larger as beta gets closer and closer to the speed of light. Everyone good with the numbers? Okay. So, if I get on a rocket ship, or I get on a rocket ship, and I travel there and back at 0.9 times the speed of light. In other words, beta is equal to 0.9. I age by 1 month. Equals delta T for me. So I'm in the rocket ship, I go there, I come back, I'm gone for I'm older by 1 month. How much older is everyone else on Earth?
Relative to you, a month younger.
No,
No?
not just relative to me. They biologically will age this as, well, yeah, it is relative to me, but they will biologically be, well, at 0.9, they will be 1 month, they will be 2.294 months older. And I will be only a month older.
Oh, so that's how that
So
happens.
it's like when we travel close to the speed of light, the time is slower.
Yes, biologically, the time is slower than people not traveling as fast.
That's crazy.
I was confused about that for a while, but now it's starting to make sense.
Yeah.
Okay, well, that makes sense.
I hate referencing those.
Yeah,
That's, yeah, it's further.
I found there are two theories about the speed of light. One is the speed of light is moves slower when in the black hole.
Oh, yeah.
Yes.
There's a children's story I'm gonna read to you right now, considering that topic since you brought it up.
Yeah, gravity does
like the